All right, 5.2 is the mean value theorem. It connects the average rate of change of a function over an interval with the instantaneous rate of change of the function at a point within the interval So the mean value theorem for derivatives. And we would shorten that to be MVT, for mean value theorem. Says if y is equal to f of x is continuous at every point of the closed interval a to b and differentiable at every point of its interior a to b, then there is at least one point C in a to b at which the derivative of f at c is equal to f of b minus f of a all over b minus a. And this is what we call an existence theorem. So that's saying that you can find the derivative of f at c by simply taking the function evaluated at one endpoint minus the other endpoint and then divided by the endpoint minus the endpoint, and that'll tell you what that's equal to. I tend to find this easier than the stuff we did in the last section. So we can have increasing and decreasing functions. So definition, let f be a function defined on an interval I and let x sub 1 and x sub 2 be any 2 points in the interval I. And then we have two possible options. F increases on I if x1 is less than x2, which would imply then that f of x1 is less than f of x2. Or the other option, f decreases on I if x1 is less than x2, implies that f of x1 is greater than f of x2. Are you down to the blue yet? Okay. So along with this, the increasing and decreasing stuff, the mean value theorem allows us to identify exactly where graphs rise and fall. So a function with positive derivatives are increasing functions. And then a function with a negative derivative are decreasing functions. Which obviously that kind of just makes sense. So in regards to increasing and decreasing functions, we also have a corollary, which is like similar to a theorem. but it's not like, I guess, I don't know how to explain it. It's kind of like an add-on to a theorem, I guess, is a good way to put it. So for that, it says to let f be continuous on a to b and differentiable on a to b. Then the first option, if f prime is greater than 0 at each point of the open interval a to b, then f increases on a to b. And 2, if f prime is less than 0 at each point of the open interval a to b, then f decreases on a to b. And we can also prove that, so I'll show you the proof for that. It's just kind of interesting.
Okay, there's 2 classes that need to be like finished, like putting in pictures, so I'll do that and then I have the list. But I need to go get my lunch for my college.
Sounds good.
Oh,
You've gone through all the other ones.
That's just 2nd grade and E3 maybe, that's not done. I don't remember why, I don't know why I mentioned it. I don't know if there's a problem. I think one of the classes I couldn't find the pictures for or something,
That's possible.
but I'll look on you.
Okay, thanks. Are you down to the corollary?
At 2.
Okay. I'll wait for you to finish that one and then we'll do the proof of it. Probably need a different color. This was stuff like this that I had to prove in college. All these theorems, had to prove them. Couldn't do most of it now if you asked me to. To be completely honest, I couldn't do most of it then either, but it's like, it's a theorem. It's already been proven. Why do I need to prove it? Like, that was my thing, but I don't know. I enjoyed proving stuff like that the square root of 2 is irrational, that 0.99999 is equal to 1. Like, you know, that one's fun because that one just 1/3 is 0.3 repeating, 2/3 is 0.6 repeating. So 3/3 is equal to 1, which would also be 0.99999. So that's why that one, you know, stuff like that I enjoyed. Or proving the Pythagorean theorem, that was cool. Proving the quadratic formula, that was cool. This stuff, but anyways, it's kind of just cool to see what one of them looks like, so. We haven't done really any proofs this year in calc, so. And in the event that you ended up having to take some kind of a calculus class, they may make you prove some of this at some point, so it would be good to having seen it before, so. Anyways, all right, so proving this corollary, let x1 and x2 be any 2 points in a to b. Say this is going to be a little bit lengthy, so.
I don't know how many just the binders, but like the rings are really big.
It's difficult to write around them.
Yeah, so they're not. Yeah.
All right, so let x1 and x2 be any 2 points in a to b with x1 less than x2. the mean value theorem applied to f on the interval, closed interval x1 to x2 gives f of x2 minus f of x1 equal to f prime of c times x2 minus x1. Okay, so mean value theorem is that f of one endpoint minus f of the other endpoint divided by the endpoint minus the endpoint is equal to the derivative at c. So just multiply on the other side, we get this. For some c between x1 and x2, the sign of the right hand side of the equation is the same as the sign of f prime of c, because x2 minus x1 is going to be positive. So whatever the derivative is, that sign, that's the sign that that side's going to be. Because with the x2 and the x1, we're always going to do bigger first and then minus the smaller, so. Then to make the conclusion for it, therefore, two options. For option 1, f of x1 is less than f of x2 if f prime is greater than 0 on a to b, then f is increasing. And option B, f of x1 is greater than f of x2 if f prime is less than 0 on a to b, then f is decreasing.
The amount that we got, she said that it would, like, come to a spreadsheet. We should have had, like, a lot more. Well, not, like, a lot more, but we're off by, like, $75. According to the spreadsheet. And then also,
Which doesn't make sense, because originally
also we
were
had
like-
some donations, too. So we were, like, shy $74 of 3,000. It's like $2,934. So she said she's gonna double check it and let us know. She said we didn't have to watch her on it, but I guess some people just didn't pay or something.
Or we mixed money somewhere. Or something.
No, I know what happened. There's a couple forms in there that the totals that are written on the forms are not the amount that they paid.
That plus we had a lot of like.
So if when we totaled them, I checked the money, but I know what forms they are because I can tell you because it's written on the back what the total should have been.
Okay.
Anyways, that's why the totals there are going to reflect what was written on the front, because when we divided the stacks up that Friday,
Yeah.
and it would be
Plus
off
that
by like
couldn't-
$50 because the person that the totals written on the front added up to like well over $50, and
Yeah.
and
Oh
I'm
yeah,
like,
because you were talking about it. Yeah. Okay. Yeah, I know what you're talking about.
never paid for her prayer partner.
Yeah.
So
There's like I think like a lot of few little things that wouldn't seem like a
Another
big deal.
question,
I
so
don't
that
know.
did you
include-
also did you add the coins in with
Yeah.
it?
Yeah. There's
It's
$50
coins
in
checking.
coin cash. The other question is the stuff that we're doing for the anything?
Already on the spreadsheet.
Are those already on the
No.
spreadsheet? And they're not in the money that we just turned in either, correct?
Right.
Okay.
Because it's just going to be leftover items basically.
Yeah. All right. Well, I don't. It's not like that big of a deal, but she's gonna double check it too. I mean, we could have miscounted.
That's what I thought the other day when I did it, but there also could be money laying around here somewhere that's for
what I'm
that.
thinking,
That's
like,
why
maybe
I'm.
it's in the bucket or in the cash box or like.
That's what I think some people.
Might have.
It's kind of like just like a hot mess.
I think yeah. So I mean, if it's, I mean, like yes, it's kind of a lot, but at the same time, I also don't think it's. I think we're gonna find it. I think we're just gonna figure out that it's somewhere
It'll end up
else.
being
There
like-
honestly could still be a stack somewhere on my desk.
And it could
My
have been
desk is
added
a hot
in with
mess.
donuts or something. Like, it's gonna even out, but it might just not be the right total for the.
We're gonna go do those really quick.
Okay, sounds good. Thanks.
Well, I need to get my backpack.
Okay, and then let's see. There's another corollary. Functions with f prime or the derivative being equal to 0 are constants. Meaning that if f prime of x is equal to 0 at each point on an interval I, then there is a constant C for which f of x is equal to C for all x in I. And one more corollary and then a definition. Functions with the same derivative differ by a constant. So if f prime of x is equal to g prime of x at each point,
In the first corollary, or the last line, is that just f of x?
yeah, this f of x is equal to C for all x in I.
I'm just like, I guess the line and the x are together.
Yeah, it kind of stuck together. There we go.
So I'm just like,
I like thought I picked the pencil up, but I guess I didn't pick it up far enough, so it just like. Let's see.
wasn't sure if it was just my eyes.
At each point, let's see, of an interval I. Then there is a constant C such that f of x equals g of x plus C for all x in I. And I'm not going to do this proof, but the proof of that is on page 204. And then the last note thing, I believe, is a definition. A function, and it's capital F of x for this, is an antiderivative. So that means that we're doing the reverse of a derivative of a function f of x if f prime of x is equal to, okay, and that's capital F prime of x is equal to lowercase f of x, okay, so the function for all x in the domain of f. The process is called antidifferentiation.